you all here tonight, and thank you for braving the incredible flood of 2017. At least that's what I hear in the weather reports. So thanks for coming out tonight. As usual, you'll have gotten a feedback form on the way in, and that's because this is an event entirely run by the Graduate Astronomy Student Association at the University of Toronto. We're all volunteers, so we really value any feedback, especially feedback about what you'd like to hear about for our next talk. As we go on tonight and you fill out your feedback forms, please also keep in mind that we'll have activities after the talk as well. Our telescopes will still be open for looking at the telescopes, if not necessarily looking through them, thanks to the weather. But we do have our worldwide telescope demonstration, as well as some 3D printed models of telescopes and our planetarium shows. If you signed up for a planetarium show online, we'll be giving you instructions about what to do after the talk. And if you just heard about planetarium shows and you'd really like to attend one, we'll be handing out tickets after the talk as well. So stay tuned for announcements on how to get into those good events afterwards. With all of my announcements out of the way, I'd like to welcome Darsh Kodwani. He's a second-year student in the physics department here, but we've allowed him to join us tonight because he studies cosmology, and it's a subject we're all very interested in. So let's welcome him to the stage.
All right, before I start, everyone can hear me? Is my voice okay? At the back? Yes. Good. So I guess you guys are the hardcore people who made it through the rain. I mean, knowing the topic, I might not have come myself. No, I'm kidding. So today I'll tell you a little bit about what we know about the universe, basically. So there's a lot of myths that go on about when we think about the Big Bang. So I'll try and move away from those and tell you exactly what we mean when we say a Big Bang, and how the current understanding, the current observations are leading to a picture of potentially showing that we might actually be living in something that's called a multiverse. Before I do that, my talk might have a lot of jargon and a lot of scientific terms, which I didn't want to use because they might not mean the same to me as what they do to you. So I decided to take a new approach that this professor does in this book of his, in which he describes what he does using only the 1,000 most common words in English. So that's what I'm going to try and do. We'll see how it goes. And since you guys, you come to these talks, I thought you might be okay with some jargon. So I'll allow myself a few standard deviations of jargon words. But I'll highlight them in red. They're basically there to make sure I'm explaining them correctly, so that I don't mislead you. All right. So let's start by discussing what the Big Bang is. So the Big Bang, it's a bit of a misnomer. The name came about from people who were trying to understand the early universe. And the first ideas were coming about, potentially because the universe is expanding, maybe it was a really small point and then things came from it. And people didn't like this idea, so they gave it a derogatory name. They're like, oh, these people just talking about bangs and everything. And so that's how the name actually stuck, the Big Bang. But it's not actually a bang. What we mean scientifically when we say the Big Bang, we refer to as a Big Bang model. It's a particular model that works up to a particular time. All right, so I'll take you back to that time and tell you how we go beyond that time today. So that's the thing to keep in mind. What do I mean by the universe? I mean everything you see around you, including space and time. So the time on your clocks and the space you would see outside if it wasn't so cloudy and rainy. That's all space-time. And all the stuff in it, that's everything that we would call our universe. So that's the universe defined. An explosion, I think, is mostly familiar with you. It's anything that's expanding outwards in a hot, messy fashion. That's what I mean. That's the scientific definition of an explosion, at least for me. So basically, the universe didn't start off, well, it might have started off as a point, but we don't know how to describe that point. So we never actually describe that moment of things coming into being. We describe things after a particular time when things already exist. So what that time refers to is the whole of space-time, which is the universe, and the stuff in it starts off in a hot state. Okay? We just extrapolate back from the time we have today to a particular time when we say the space-time came into being and the stuff in it was hot. That's what we mean when we say the universe started. There's no actual explanation of how things start. We don't have that yet. What we have is this point of time where things come into being and they're hot. This point of the beginning of the universe is remarkably simple. The state that the universe is in initially is very, very simple to describe. It's simplest than almost anything you can think of. Even the simplest atoms are more complicated than it. So let me show you what it would look like. So here's space-time, basically, this black region. This comes into being. It has stuff in it. So these spots refer to fluctuations in the temperature. So particular regions of space are actually hotter, and particular regions are colder. In particular, the blue dots represent hot regions of space. The orange ones represent cold regions of space. And you notice that there are different sizes of spots as well here. That's important as well. I've drawn this deliberately in such a way that you should have approximately the same number of hot and cold spots, the blue and orange ones, and the same number of spots of the different sizes. Okay, because that's how the universe actually began. And one further thing we know is that it was expanding. So it was expanding. Okay, and that's the Big Bang model. That's it. That's all there is to it. You assume that there's space-time. You assume there's stuff in it. Most of it is hot, but the regions where some places are a little hotter and colder are defined by these small balls. We'll get a bit more technical after that. And you have these fluctuations on different scales. Okay? You have these different sizes of balls, as you see here. There's one this big, there's one this big. I've only drawn two, but they actually exist on all scales. All right? And that's it. That's all we know about. That's what we mean when we say the Big Bang. Okay? You can describe all of the things that I was saying by a few numbers. Depending on who you ask, they could be up to 6 or 7 numbers that describe this initial state of the space-time and stuff in it that's hot and fluctuating. So here are the numbers. I will refer to these from time to time, so I thought I'd just list them. One of them is called AS. It corresponds to, in the previous picture I had, to the color of the ball. In particular, whether it's hotter or colder, how blue is it, or how red is it. NS is another number. It corresponds to the size of the balls. So if NS is 1, that means you would have exactly equal number of balls on each size. So that's what it means. It corresponds to the number of balls of a particular size. All right? This omega n corresponds to the energy carried by different species of particles. So that's a little bit technical to explain, but let me try. You have different types of particles. You can have hot particles, you can have cold particles, you can have particles that don't interact gravitationally, some that do only interact gravitationally. And this omega n can stand for n number of these species that interact differently. We will only need 2 of them for today. But you can have, when traditionally the way you write this down, you include something called the cosmological constant as well in here. And so you'd have 3 or 4 numbers that omega corresponds to. But for our purposes, we'll only need 2 hot and cold ones. This tau is interesting. It refers to what's called the opaqueness of the universe. Or in other words, how far can light travel without being reflected, basically. So it corresponds to the usual notion of what opaque means. It means how far can you see? When you look through a foggy region, you can't see very far. It's rather opaque. So that's exactly what this opaqueness corresponds to. This is actually not what's known as a fundamental parameter, in the sense that when you look out at the universe, we make measurements, as I'll come to talk about. You don't actually need to have this parameter. In principle, given the other 4 parameters and the equations that we get from physics, you can actually predict this parameter. It's just too difficult to do it. That's why we end up using it as a free parameter that you would fit to the data. So you look at your experiment, you look at your equations that describe what you see, and you have to match them to some parameters in the equations. And we use this as an additional one, but that's not necessary in principle. It's just too hard to do it otherwise. And H0 corresponds to the expansion rate of the universe. Basically, how quickly is the universe expanding? And I mean literally, the space and time themselves are increasing in size, all right? It's not stuff in the space-time, it's actually space-time that is expanding. It's like this entire room would be expanding, for example. So these are sort of 5 numbers that I'll come and refer to, and I'll mention them when I come to them. But these numbers can describe everything you saw, everything that I described before about the early universe. So this is just a summary of what I said about the particles. So there are two types of particles. There's hot and cold particles. The hot particles are like heating up water, basically. And so if you heat up water, you get steam. And steam then pushes out. Okay? It has a pressure. So basically the hot particles, the only thing you need to know about them for this whole talk is that they will be pushing out. They have a pressure. They exert a force outwards. Okay? The cold particles are ones that do not have this pressure, but they have mass. They have a property of mass, which means they will gravitate, which means they will pull things in, okay? So one type of particles are pushing stuff out, and the other type of particle is pulling stuff in by gravity, okay? So the hot ones are pushing things out, the cold ones are pulling things in. Now the fact that these two things exist means you end up having oscillations in the universe. What do I mean by an oscillation? Well, I have a nice video to show you. So imagine this bubble is the actual entire universe. The fact that it oscillates like this, once you put some force in it, is exactly what I refer to as an oscillation in the early universe. In fact, the early universe could actually have looked something like this. You'd actually have particles in it. The whole thing is oscillating because the hot ones are pushing this bubble outwards, and the cold ones are pulling the bubble inwards, and you would end up with this type of oscillation. That's actually what happens. You can take the equations that describe this of thermodynamics, of gravity, and you can work out that you would find these types of oscillations. These are called acoustic oscillations, but that's another word that I didn't want to use. All right. So now that we have this picture, the question is, how do we know all this? I mean, I've been telling you all these facts, right? I mean, about this happens, this happens. But how do we know this? And the reason we know this is you can describe the equations very precisely, and you can predict what would happen, and you can make a measurement of what would happen. So at early times, as I was saying, you have that parameter tau that determines how far you can see, how opaque the universe is. When it's very, very early on, the universe is too hot, which means that basically your atoms, which are formed of a nucleus which is positively charged, and electrons which are negatively charged, can dissociate. So positively charged and negatively charged, well, what do? Somebody tell me. They attract, right? That's right. So they should be bound together in an atom. That's how stable atoms form. But because the early universe is hot, as I say, this is the Big Bang model, it starts off as hot. What happens is that these particles, the electrons and the nucleus itself, has too much energy. That means it can move quicker. It can escape its own binding energy and therefore dissociate. So what you end up with is what's known as free charges. You have electrons and neutrons and nucleons that sit around by themselves. Now that has a specific effect on photons, which is light. Light is also called light photons because that's another name for it. And the light actually bounces around if you have charged particles. It can just literally reflect off different charged particles, and it just gets stuck in this sort of a scenario. So imagine you fill the room with all of these charged particles. Literally, you wouldn't see anything. And so this is why the early universe is opaque. This is actually what determines that parameter tau, right? As I was saying, it's not actually a free parameter. You can actually calculate it, but it's just too difficult to calculate it because you need to keep track of sort of all of the particles and everything that happens, which is too hard. So that's why the early universe is very opaque, and you can't see anything. But after it expands enough, when things expand, when a gas expands, it cools down naturally. And when the universe expands, it also cools down. And when it cools down, basically this attractive force, as you said, these things should attract each other, is sufficiently large that the atoms can recombine and form neutral atoms. So you end up with this neutral structure here, in which the electrons and the nucleons sit together, and overall the light rays don't see any charge. Okay? Like now there's no charge. So the light rays can just stream forward without having to bounce off anything else. That's what happens. And at this point, the universe becomes transparent. In fact, this is the first time light can travel through the universe without being reflected off other things. This particular thing is also known as recombination, but let's look at this picture first. So imagine we're sitting here in the center. As you look out in the universe, you also look back in time because the light travels at a fixed speed. It's not infinitely big, it's just fixed, which means it takes a lot of time to look back. So when you look really, really far away, you're actually looking at those things as they were a long time ago. So as you sit in the center here on the Earth, we look out and we look really, really far into the sky. We can actually look right back to the time when these first light rays, these first photons were emitted. Basically, when the universe goes through this transition of going from opaque to transparent. And that first light is known as the cosmic microwave background. So here's just a summary of what I said. This happened approximately 380,000 years after the Big Bang, actually 379 for the pedantic in the office in here. So it's actually, you might think that's a long time, but you have to remember the universe is something like 13.7 billion years old. Compared to that, this is a very early time. The universe's temperature was also very, very hot at this time. And this is the light, the first light that you can see. And it's called the cosmic microwave background radiation, so, or the CMB as we like to call it. The reason we have the microwave bit in there is because when the light is emitted, it has a particular wavelength, and as the universe expands, it stretches the wavelength as well. It's the same effect that would happen, if you're standing beside a road and an ambulance goes by with a siren. The siren emits some waves, and as it comes closer, you hear the pitch increase because basically the waves get stretched out or squished together depending on how you are moving. And because the universe itself is expanding, there's some motion, and that causes it to stretch out into the microwave range. All right. So here's a picture of the CMB. This is a real image. This is not a cartoon. This was taken by the Planck Satellite. There are a lot of people here who work on that. In fact, some of the pioneers of how to make these measurements work exactly here. And so this is actually a real image of what I cartoonly drew in the first few slides. It's projected out on the globe as we would see it. And here you see the same spot structure. You see these hot and cold spots. The red ones are colder, the blue ones are hotter. And statistically, even though you might, when you look at it at face value, you might think this region is hotter than this one. But statistically, on each scale, when you calculate, how similar the temperature is, it turns out to be the same everywhere. And these differences that you see are actually only 1 part in 100,000. They're very small. Overall, if you didn't exaggerate these spots, you would literally see a flat sky. You wouldn't see any change in temperature. So it has an interesting history how this was discovered. It was discovered in the 60s by these two folks at the Bell Labs. And they were actually looking for radio waves from the sun. They weren't actually interested in this. And so first, before you do a measurement, and in general, if you do a science experiment, you have to calibrate it. What does calibrate mean? It means you need to know, before you're looking at the object that you want to describe, that all the other signal that is there, you need to know that, so you can subtract that, right? I mean, otherwise there's no way of knowing where the signal is coming from. You need to subtract what's already there. And that's what they were trying to do. So they took their telescope, they pointed it at different regions in the sky, just to calibrate, well, how does it look here, how does it look here? So I can subtract that signal. And no matter where they looked, they always saw this constant signal, a constant beam of microwaves that was coming at them at a very fixed temperature. And they didn't know how to interpret this. They were really confused. They didn't know if it was an atmospheric effect. They even thought that there were pigeons that were living in the actual telescope. And they thought maybe it's pigeon dropping, so they went in and cleaned it all out, and the effect was still there, and they didn't know what to do with it. Then it turned out that they had to be told by some of their colleagues at Princeton, who were trying to make precisely the measurement of the CMB. And they had to be told by them that, look, what you've actually measured is the first light in the universe, not some terrestrial interference. So it was actually discovered by accident, the CMB. In fact, a lot of these things happen by accident. It's kind of interesting. And here I like this picture. So this guy is Alexander Friedman. So he also used to study the universe very early on in the 20s and the 30s. And he of course had no data, because this is the first time a measurement was made. This is when cosmology really became an experimental science, right? Because this is the first time you could actually look and make measurements. And I just want to point out, the clear difference that you see in expression when you don't have data to when you do have data. It's quite striking, right? I mean, it's crazy. This theme will come back. And it's not just because he was Russian. I mean, we'll check that. We'll test that hypothesis too. It's quite striking. Which one do I resemble? I mean, anyway. So that was the first time the CMB was measured. But you can actually, you know, what it measured was an overall signal. But the picture I showed you about the Planck satellite, that is a very detailed picture in which you actually measure the differences in temperature at different spots. And this is what this image shows. So let me explain what this graph is. So I take my telescope, I point it at this point in the sky, right? I make a measurement of what the temperature of it is. And then I point it over there, and I make a measurement of what the temperature is. I compare how well do the temperatures match. You have to do this statistically. It's not just one number that you get from here, one number that you get from here, because you get a map of the whole sky. And so you do this statistically, but you know, this is exactly what you do. Statistically, you take one point and you correlate it. Correlate is the technical term for just comparing the 2 points. How similar or dissimilar is the temperature of 2 points on the sky? And this is a plot that tells you, depending on which scale you look at, how similar they are. So look at the top, the horizontal axis, but the top label, it's angular scale. So this is 2 points that are separated by either 2 degrees, 0.5 degrees, 0.2 degrees on the sky, and so on. Okay? And this curve, the vertical axis, represents, in some sense, it's in what's known as Fourier space, so it's a little hard to interpret immediately. But what it tells you is how similar or not are those 2 points on different scales. So if I look at two things at this scale, so I move this whole thing over here, now compare these two, now compare these two, and so on, then I basically count up how similar or dissimilar these things are. And I get a plot like this. You can't even see, but so these black dots are what Planck has measured. Okay? That's what Planck has measured. There's actually a thin line, I mean, I can barely see it, that is a prediction of the Big Bang model in which you input these parameters. Okay? Remember, you have to give it those 5 numbers that I wrote down. Okay? Those 5 numbers have to be put in, but you have all the equations. You just need to put the numbers into the equations. And the way you do it is you take this data and you match the numbers to the equations that you have, and then it fits almost perfectly if you give it the right 5 numbers. I mean, you can't even see the difference, right? I mean, look how well the dots lie on this line. So this red one corresponds to the small uncertainty that you would get in your model. But basically, think of the red one as your model, and the black dots as the experimental evidence. And you see they match almost exactly. But remember, you have to put in those 5 numbers. I keep saying that, and I'll come back to it. If you're interested into why this happens, I'll try and explain later. It's a little bit technical, why there's this big region over here. One thing I want to point out is that you see these really nice peaks. And these are actually exactly because of the reason of those oscillations. Again, if you have a question about how these actually happen, I can answer that later. But these come about because you have these oscillations in the early universe, because things are getting pulled in and pushed apart due to the hot and cold particles. And this is an exact prediction that would come from that physics. And this is just a summary again of those peaks. And the most important thing about those peaks is that those peaks exist, mean the oscillations on each scale have to be in sync. That's what it means. Again, that's actually a little bit too hard to explain. But if you don't have the oscillations on each scale, so if I look at this region on the sky and this region on the sky, if they are not oscillating in the same way, if they're not in sync with each other, then you would not see this peak structure. Mathematically, it actually corresponds to the fact that all the energy in the particle species, in the different particles, the hot, cold ones, they actually have to have the same amount of energy. This property, I'll tell you the name, but you wouldn't need to worry about it. It's called the adiabatic. You say that the perturbations, the fluctuations in the early universe are said to be adiabatic. And that's a property that leads to this structure. It's actually something I've spent a lot of time studying, so I can try and answer that later if you have questions. But anyway, so let me just summarize what we know about the Big Bang so far. The Big Bang is not a bang. It's a point in time when we say the space-time comes into existence. You have stuff in it. It has fluctuations. Some regions are hotter, some regions are colder. And we know the space-time is expanding. Okay? That's a summary of the Big Bang model. And the evolution of the particles that exist in that early universe, in that hot region, gives rise to this spectrum you saw, this experimental thing you saw here. And these peaks, known as acoustic peaks. So that's basically it. That's what we know about the Big Bang. This is it. When someone tells you what the Big Bang is, scientifically, this is what it is, okay? It's a time when things came into being, things are a little bit hotter and colder in different regions, and you have slight fluctuations on different scales that predict this spectrum. That's what the Big Bang model is, okay? That's what a cosmologist means when he says Big Bang model. And that's the limit, that's what I would say is, you know, the hardcore limit of our understanding. Yeah. That's as far as we can be sure of, that we would say, we understand the universe well enough to say, this is really how it happened. Beyond this time, it becomes a little more interesting, and that's what we're going to go on to. But before I do that, there are a couple of problems that the Big Bang model also has. So the main one is that the temperature, as I was saying, is actually almost exactly uniform on all scales. So I look here and I look here, and the temperature is almost exactly the same. It only differs in about 1 part in 100,000. Okay? And this is very strange. We don't. It's not just that it's aesthetically not a nice thing, because aesthetically you might think, oh, it's good that you'd expect things to be very similar. But when you think about it, the way we would think about a physical system, the only reason such a thing should happen is either that initial state comes from another state that was previously had everything in it, which made everything the same, or you need some time for things to equilibrate. Now let me explain equilibrium, which is this red word here. Equilibrium basically means, if I take a candle and I put it here, the temperature in the whole room isn't going to change instantaneously, right? This region of space will, this air will get hot, but it takes time for the heat to diffuse out to the whole room, right? It takes time that's known as equilibrium. That process of the temperature increasing from one spot and diffusing outwards is known as equilibrium. And that takes time, because the way that works is the air molecules around a particular region need to get hot, and then they move more, they move quickly, they bounce into other ones, they transfer their energy onto other ones, and then they move a bit, and then they bounce into something else, and so on. So it's a process that happens slowly. Of equilibrium, and that needs some time. And the quickest that you could have equilibrium, even just the simplest thing you would say is you need at least time to send something over to the other side of the room, right? Otherwise, if you can't even send anything there, how could you be in equilibrium? And that's basically what happens in the sky. It is actually impossible for the whole sky to be in equilibrium during the emission of the CMB. 380,000 years after the Big Bang. That's not possible, for the simple reason that if I look at one region of the sky here, and I look at one region here, to equilibrate, I need to send at least something from one region to the other. Now, if you extrapolate at how far those two regions are, there's basically not enough time for even light, which is the fastest thing we have in the universe. It cannot go from one region to the other region in 380,000 years. Basically, so here's one point. This is a light ray, and that's the distance it can travel, for example, in 380,000 years. So there's no way that it can communicate with it. And so there's no way that things could equilibrate. That's a problem. I mean, you need to solve this problem. Either you just assume that it starts off as it is, which is not a very nice explanation, certainly if you want to describe things, why are things happening, or you need to somehow get equilibrium, but you can't have equilibrium. So it's a problem. This has always been a problem with the Big Bang model. And the solution to this problem was proposed by this man. His name's Alan Guth. He's a professor at MIT, and he proposed a simple solution to the problem. He said the following. He said basically, if I look at two regions in the sky, as I look at them now, let's say it's this distance on the sky. Now, if earlier on these two things were here, and they were stretched out really quickly to these two regions, and we can only see these two regions now, then it would seem to us that these two things, they're very close to each other, but they can't have equilibrated because we don't know about the phase before when they were really close, right? You all see that, right? If two things are really close now and I just stretch them apart, but I don't know about it because I can only see things at this point when they're stretched apart, then there's nothing I can do. There's no way I can, disentangle that piece of information and say, well, how could these two things happen? And that's basically what he said. He said, I'm going to assume that these two things were really close and were stretched out. He actually did it for a problem, is to assume that before this expansion of the universe, that it's slowly expanding out at a constant speed, the universe was before the Big Bang state was actually accelerating in its expansion. So you assume there's something there before this thing we call the Big Bang model. So this goes beyond it. So this is the first attempt at going beyond the Big Bang model. And you assume that there's a state before it in which the universe is accelerating, okay, in its expansion. It's literally getting stretched ever more quickly. But we have no access to that region. But if something like this did happen, then you can solve this problem of things not being in equilibrium. It actually solves a couple more problems. Well, some people think they're problems, some people don't. So I haven't mentioned them in too much detail. So this was his solution to the issue. And as some of you may know, you must have seen that to have acceleration, you need some form of a force. You need something to push the thing. And a force can only come from some energy, which means that you need to postulate, you need to guess that there was some form of different type of energy in the early universe that we don't know about that caused this acceleration. And he provided a mechanism. He didn't just say, assume this happens. He provided a mathematical explanation of how this could happen. Before I do that, there's a nice extract from his diary. This is his diary, Alan Guth, and in 1979. I mean, he'd been working on this for several months, so it wasn't just like he had this idea immediately. And apparently when he put it all together, he wrote this down in his diary, which he always talks about. He says, a spectacular realization. And he says, this kind of supercooling can explain why the universe today is so incredibly flat, and which is in some way related to why it's so uniform. And the fine-tuning paradox, that's a different paradox. That actually wasn't a paradox. But so, I mean, the supercooling comes from the fact that it's expanding ever more quickly, which means it's cooling ever more quickly. So in fact, before this time of the Big Bang, the whole thing I described before this, I assume it starts off in a hot state. Before that, the universe was actually very cold. And there's a process from which it gets hot, and I'll describe that. So yeah, this is just a nice action. Hey, here's our friend Friedman again, and Alan Guth. Yeah, much happier. So how does inflation work? So as I say, you need to have this type of acceleration, you need to have a different type of energy. And this type of energy is given a name. It's called the inflaton energy. And it's very different to the types of energy normal particles, the stuff that you and I are made of, carry. Until this was thought to be very, very hypothetical, until we discovered what's known as the Higgs particle a few years ago at the LHC in 2012. And this particle, the Higgs particle, actually has the exact same type of energy as the simplest inflaton energy would be. So it seems a little less implausible now. But people have actually tried and still do try to construct a scenario in which this Higgs particle is exactly the thing that causes this acceleration. But there's no sort of accepted version of that yet. But people do try that, so it's something people try. It's called Higgs inflation. So how does it happen? So I can only do this by analogy, because the mathematics is a little bit involved. Assume you have a ball that's on top of a hill, and it's rolling down the hill. Once it's at top of the hill, it has what's called potential energy, right? Is everybody familiar with this idea of potential energy? Energy is this ability to do something, this ability to move something is basically all you need to know about energy. It's just if I have energy, I can move something, either myself or something else. And when you're on top of a hill, you have the ability to move yourself, right? You can just roll down. You can start moving. And so your potential energy then gets converted into kinetic energy. And that's basically what happens with this inflaton field, is that this vertical axis represents its energy, its potential energy, and it sits on this potential that looks very much like a hill. Once it's up here, it doesn't move very much. This is an assumption. This is an assumption, okay? This is all a hypothetical assumption about a model that we're going to construct. You assume there's this Higgs particle, sorry, not the Higgs particle, there's this inflation energy that exists on top of this hill region. If it doesn't move very much, when it's at the top, it has a lot of potential energy. Now, because this is pre-Big Bang, there were no particles that we know of. We don't understand that period. So we assume that this particle dominates the energy of the universe. Okay, it is most of the energy in the universe comes from this particle, And you just construct this energy in such a way that it causes an accelerated expansion. So while it's on top, it causes accelerated expansion. As it slowly rolls down here, it loses its potential energy. So the acceleration starts to slow down as it rolls down because there's less potential energy. So the universe itself starts slowing down. And once it gets to the bottom, it basically dissipates its energy. Now, the way it dissipates its energy is not very well understood, but in the same analogy, if you roll the ball down a hill, eventually if it's in some sort of a plateau region like this, we know it's not going to continue to oscillate, right? There'll be friction and it'll lose its energy to heat or whatever else. And basically the inflaton particle does the same, and that process is how we think, this model, I should stress, in this model, is how we think the particles and the heat in the universe that we call the Big Bang comes into being. So it's a nice story that you can describe mathematically. Up here it causes the acceleration. As it rolls down, it slows down. Once it comes to the bottom, it dissipates all of its energy into the particles that we see because it loses all its energy. All right? That's the basic picture of inflation. And how do we know this? Is because simply, if you have this one type of inflaton energy, it naturally predicts this peak structure. If you remember, in the Big Bang model, I said that when you have this peak structure, you have to put in those 5 numbers. Remember? These are those 5 numbers that I told you. I have them somewhere. Maybe not. But basically, you need to put in some assumptions about those 5 numbers. And this inflation model allows you to put in those 5 numbers. It's very nice. It's a very nice model to predict those 5 numbers, if you like. It doesn't predict all of them. It predicts some of them that allow this peak structure. Okay. In particular, the fact that this peak structure is coherent. Those things I call adiabatic fluctuations. It naturally predicts what's known as adiabatic fluctuations, which just means each particle has the same amount of energy. But that's only with the simplest models of inflation. So that's why a lot of people get very excited about it. They think, well, this is clearly how the universe began. Now, I remain a little bit agnostic and skeptical about it. I don't think we have enough evidence yet to say that. But people still go on and say these things. But there are many problems with it as well. For example, it also naturally predicts that you should see what are known as primordial gravitational waves. So gravitational waves, as you've heard about probably, are these fluctuations in space-time. And it naturally predicts that these should exist from the very early universe, but they haven't been detected yet. In fact, in 2014, some people thought they had detected it in this pattern. I don't really have time to explain how this happens, but they thought they had observed this. And if this is observed, this is almost, this is the best evidence you can get for inflation. And if you observe this type of evidence, then it's almost inevitable that you would have to have some process like inflation. But we haven't observed it, but the search for this continues. There are several issues with inflation, though. It's not actually one model. It's actually a whole range of models, and that's the issue because you can't really make predictions through it. That's my main problem with it. And the other thing is that even though it predicts this peak structure. It doesn't predict a lot of the other numbers well. In fact, some of the other numbers that the simplest models of inflation predict aren't actually correct. So it's sort of on the borderline of whether it is really how it is or the universe began in some other way. But some people can be extremely for it or extremely against it. You can get both camps, as with everything, I guess. There is one major problem with it, which leads me on to my final thing in the last couple of minutes about the multiverse. And that's the problem. This wasn't actually realized when Alan Guth first came up with it, that once you have inflation, you can't actually stop inflation. So this model of the early universe, because you have this inflaton energy that's rolling down here, and the energies in the early universe are very, very hot, even though it cools it down, but when inflation itself started, the energy was very hot. It should have what's known as quantum behavior. Now, I have no time to explain what quantum behavior is, but all you need to know is in quantum mechanics, things can have motion even when they have so to speak, no energy. They can move around, they jitter around in their motion. And so basically when this particle, this Higgs energy can go down this hill, it can from time to time jump up. a little bit. And if you recall, the vertical axis corresponds to the energy, which corresponds to how quickly the universe is accelerating. So if you jump up or down, that is determining how quickly you are expanding, the universe is expanding or not. And basically what happens in inflation, this is inevitable. This was realized a few years after Alan Guth's first idea. But it is very, very concrete that this is inevitable, that if you have inflation, you will have this process that this energy would jump up. And what would happen then is the space-time is expanding, let's say, and suddenly the inflaton particle in one region jumps through this quantum process a little bit. So this region of space-time suddenly stops accelerating as quickly as the other it. So it just becomes like the small region, and the rest of it continues to expand at an accelerating rate. And you end up with this process where imagine the whole region here is the space-time expanding, and these bubbles that you see are the regions where the inflaton, that particle, has jumped a little bit on its motion down that hill. And so these different regions actually stop accelerating as quickly, and then they just decay away like the normal inflaton does, whereas the rest of the space-time around it continues to accelerate. Just keeps on accelerating, which means that you cannot actually send any light from one ball to the other, which means you cannot communicate because the space-time continues to accelerate between them at an ever-accelerating rate. And if that's not bad enough, this process happens ad infinitum. It doesn't actually stop. It just keeps on happening. You can't stop that from happening. And this was a realization that really, puzzled a lot of people. So you'd have these pockets that would just come into being, and because they stop accelerating as quickly and the rest of the space-time continues to accelerate. And you would end up with all these pockets. And these pockets are what were known as pocket universes. And if this is true, we would live in one of these pockets. And that's where this idea of the multiverse comes from, in that you have lots of pockets that come into being because they don't accelerate as quickly as the rest of the space-time, and therefore end up just really, really far away. So this was the first reaction of most people when they heard about inflation. And it's a nice model too, that this space-time is inflating away, and this region is not inflating. And as I say, almost any model of inflation that you can think of naturally predicts this. You can't get away from it. So each of those bubbles will have different of those 5 numbers that I told you about initially. It has different numbers, and we would live in one of those numbers. This, for some people, is very appealing. I am not particularly keen on it for reasons that I can explain if you ask me later. Basically because it becomes hard to count probabilities when you have an infinite number of things happening. And the main issue is that you can't communicate with the other pockets. So how do you even know? Is there any way you could verify this? And that's my final question. So it's more of a philosophical question. It's sort of a unique position that we've been in science, that a theory predicts things that there's no way even in principle of knowing. That you cannot communicate with one pocket from another pocket. So how do you know you would be in a universe, in a multiverse? And the only thing I can say to that is, a theory is never tested in all of its, in every way, right? You can never test a theory in every prediction it makes. You can only test certain predictions. And if you make lots of predictions and a lot of them agree with the experiment and none of them disagree, importantly, if you cannot find an experiment that disagrees with the theory, then you have to start taking it seriously. And for example, if you saw these primordial gravitational waves, these early fluctuations in space-time, then you would you would say, well, that means inflation was true. And if inflation is true, this must also be true. So you're sort of stuck in that situation because if, you can't take one part of a theory and say, the rest of it I don't believe because it's predicted by the same thing. So we could end up in that situation. Do I think it will happen? I don't know. If it will happen, it'll happen pretty soon because there are a lot of experiments that are looking for these gravitational waves, primordial gravitational waves. So we'll see. And of course, I have to end with a picture of this is Andrei Linde. He's the one who described this multiverse model. And he is Russian too. So clearly, that's not the distinguishing factor. Yeah, so anyway, I'll end with that. Thanks a lot.
Thank you, Darsh, for tackling such a broad topic in such admirable detail. See if you've got any
hope I did well.
from our audience.
Yes. Yeah.
So, well, I understand with this multiverse theory, does that they said different parts of space expand differently, and others, and then branch off in the bubble. So I have two questions.
Yep.
So one is that related to the, I guess, for lack of a better term, like science fiction starting with cat multiverse, where it's like every action you do makes another universe, where I didn't drop my hat. Are they connected, or are they like incompatible with each other?
Shall I answer your first one, or do you want to ask the second one too, at the same time?
Oh, at the same time? Okay, so the second question would be, if different parts of space are expanding at a slower or faster rate and then disappearing into bubbles that we can't communicate with,
Right.
will we notice regions of space like not expanding normally and then disappearing?
Would we not notice that? Is that what you're asking?
Yeah.
Okay, so let me start with the first one. The answer for the first one is that there are different types of multiverses that physicists talk about from time to time. In fact, there's a book by a physicist, Max Tegmark. He has a book called The Mathematical Universe, in which he actually has categories of different types of multiverses. So you can read that if you want. And the answer to your question is that the universe, the multiverse you're describing is what's known as the many worlds interpretation of quantum mechanics, in which, as you say correctly, in quantum mechanics, when you make a measurement, before you make a measurement, a system can be in several states. And when you make a measurement, you only see it in one state. So this cat thing, this cat can be both dead and alive. And when you make a measurement, is it that in your universe, you just see it to be dead or alive, and in another universe, it exists as both states. This is not the same thing. It's very different. It is completely compatible. I mean, it is totally compatible with it. But depending on how much you like or dislike multiverses, that can only make this worse, because in each of these multiverses, you would have, that multiverse is exponentially increasing in the number of universes, because, so the state that a quantum state in most cases has, almost infinite number of states it could be in. It's not just as simple as a cat being dead or alive. It can be sort of everything in between as well. And in that multiverse, you literally, at each instant, you're making almost infinite number of universes. So that's a really big multiverse, a really, really big multiverse. This one would be smaller if you didn't have that, but if you combine the two, you'll have a really big multiverse. And to your second question about, what was it again? I shouldn't have asked it. And wouldn't you see it? That's right, yeah. Wouldn't you notice? The answer is no, you wouldn't notice, because they don't. What can happen, here's the following thing that can happen. Let's say you have this big space-time, and this region stop accelerating as quickly. So they form these pockets. Now, if this pocket disappears, firstly, okay, that can happen, but nothing it can do can influence this guy. You have already detached from it, right? You have already detached from it. At that point, that's by definition almost. It's almost by definition that if you're detached from it, then you're a pocket universe. What can happen in some cases is that you can have bubbles that form real close. This whole process, I describe it like, it's sort of just bubbles in it. But this whole process actually happens in water. This process called bubble nucleation actually happens in water. It's the same mathematics that actually leads to this. Very, very, almost identical mathematics. In fact, one of the people I work with, he wrote a paper on how these two things are exactly the same. And in that case, what can happen is if bubbles form close enough, they can actually collide. But in that case, that doesn't usually happen in, I'm going a little bit off topic, that doesn't usually happen in 4 dimensions. You have to have a very strange type of gravity for that to happen. But that can happen in principle. But you can never see things disappear, because by definition almost, in this case, they would be detached. Sure.
Okay, so
Yeah.
particles are expanding equally. My take is one of those particles is a gravity particle, and it slows down to build its gravity field. And another one is a magnetic particle, and it slows down, sets up its magnetic field.
Right.
So that's so they're setting up shop in this flow that's going on. That is almost inevitable that happens. Particles that just gravitate will gravitate and form stuff around them. That have strong magnetic fields will also form structure around them in more complicated ways. What I was saying was not actually that the particles themselves are moving apart. It's the space-time between them that's actually accelerating. The particles may move too, Okay, so
Yeah.
in the space,
It's actually it's literally the space and time, the space between them that's expanding.
okay, so in there,
Yep.
floating around unseen to the eye is this gravity field that shows up and magnetic and electric
Sure.
fields.
Those will
They
exist.
just come out of nowhere, or just part of that field. So once they do, then the bubbling starts.
No, so the bubbling, the magnetic and the gravitational field is a little bit more tricky. But the bubbling, this magnetic fields, the electric fields, the strong forces, the nuclear forces as we call them, they only come into being once you are in a bubble. Okay? The bubbles are dominated by the gravitational interaction, but once you have a bubble, this inflaton particle that I said, so this guy actually has to reach the bottom. In most of the cases, this guy has to reach this bottom region for these particles, the electric and the magnetic particles, to come into being. So this guy has to reach the bottom, decay into those things. So that can only happen inside a pocket.
You better give someone else a chance to ask Darsh the hard questions.
Okay.
This guy's in the front's been waiting for a while.
Sure. Yes.
So if this multiverse does exist, how big do they think it is, and how many universes do they think are in it?
It's a hard question. In most cases, it's actually just infinitely big. And there's different sizes of infinities, but I don't actually work on it because I don't like it. Ironic, right? So I don't have a good answer for you, but in most cases, it's infinite. In certain models of gravity, you have people who claim that you have 10 to the 500, so it's a finite number. It's only 10 to the 500, I mean, so that's 10, 1 followed by 500 zeros, right? So it's a finite number. But some people say it's a finite number, but that's actually not referring to this particular case. In this particular case, it's almost always infinite. Yes?
Would you expect to have the same physical laws in each of these, or should they have different?
Great question. In most cases, you wouldn't, because this inflaton particle, when it gets down, it has to decay into the forces that we see, and it can do that differently in different universes. Sure, you pick, yeah. Hey.
So if our universe is a region that is expanding at a different rate from the rest,
Mm-hmm.
and the CMB is information from the beginning, is there a way to have information in it that is related to the larger
system? No, there is no way the CMB can carry information about the bulk system, the overall system. The only thing the CMB can do is, as I was saying, if you have this collision between two bubbles, is that can affect the CMB, because the bubbles, you have to remember, the CMB can only exist. The CMB will be different in different pockets, and it only exists inside a bubble, right? And as I say, by definition, once you're inside the bubble, there's nothing you can do to communicate with anything else outside your bubble, by definition almost.
So that means that the regions in our universe that are going at different rates are effectively becoming universes?
But that's the point. In our universe, the acceleration is the same everywhere, as far as we know. Yeah, but you're right. If parts of it, I mean, that's a good question, because the fact is that recently in 1998, it was discovered that our universe is accelerating now. Its expansion is accelerating, which means that there will be a point at which you cannot see certain regions of space because they're just moving quicker than the speed of light. And at that point, it's a good question. It's the question, would you call those regions of space different universes? I mean, this is the same question in some sense. That's what I'm saying. That's what people call a multiverse. But in some sense, it's not really a multiverse. It's just the same thing, just different regions that can't talk to each other. But they will have the same laws of physics still. So in that sense, it's not quite that. But
We have a question down here.
yes.
Yeah. Okay, you obviously want somebody to ask this. Why don't we like the multiverse food?
Why? I mean, the thing is, in some sense, it's very. It's not that I don't like it. I just don't really know how to work with it, and nobody really knows how to work with it. That's the problem. It's very nice in some sense because it allows you, in a very natural way, to explain a lot of the numbers in our universe, like, why is the charge of the electron what it is? Well, the answer is that there's just almost infinite number of different ones. We just happen to live in this one. And that sort of seems very natural, because if you ask the question, why is the Earth at a certain distance from the sun? That's not a fundamental question now, because we know there are lots of planets around us, around different stars. We just happen to live in one where, we're suited to live. So in that sense, it sort of works. What I don't like about it is, firstly, it's not observationally as well tested. There's not enough evidence to really, believe this sort of a thing. It doesn't have enough pull for the small amount of observation. And calculationally, the issue is, in this multiverse scenario, you can't count probabilities, as I was saying. There's this thing called the measure problem, in which once you have an infinite number of things happening, physics is about predicting things, right? Physics is about predicting certain things, or at least giving a probability for something happening. I check my phone, it tells me it's 100% that it's going to rain today, or whatever. But in a multiverse, it's not clear how you do that. It's not clear how you predict things, because everything is happening an infinite number of times. And at that point, it becomes difficult to do calculations. That's probably why it seems very aesthetically unappealing.
One last question at the top left there.
Yes, I was watching the famous documentary about the Large Hadron Collider.
Yep.
And some scientists have hypothesized the weight of the Higgs boson, or the existence of the Higgs boson. And obviously, the calculations didn't come out precise. And so that led to some conclusions that arose that said that the proof for the actual existence of the Higgs boson and other fundamental particles are not within this universe, but rather maybe other universes. Would you say that's actually legitimate scientific with what we have proof that the multiverse could exist? Because we really can't find the building blocks within our own.
Firstly, I wouldn't say that I would not take that as proof of a multiverse. I simply wouldn't do that. I'm not sure how you would. First, I might not just know enough to answer the first part. That I'm not entirely sure how you calculate the mass of the Higgs boson. You can't really do that. The standard model, which is what you use to do these calculations, I mean, there's some regions that naturally you would think it would be in, but there's no calculations really that tell you the mass. So yeah, I mean, I'm afraid I don't really have a good answer to that, but I certainly wouldn't take that as evidence for a multiverse. You need, I don't know whose quote it is, but there's that famous quote, right? That extraordinary claims need extraordinary evidence. And right, and we certainly don't have extraordinary evidence for this.
And it is an extraordinary claim. Before I let you all go, I have a few announcements to make. If you signed up for a planetarium show, you're going to need to meet your planetarium ambassadors, who are standing at the back of the room and waving at you now. They'll meet you in front of the elevators that are just as you walk out of this room and continue through the doors past the stairs. If you want to pick up tickets for a planetarium show later tonight, we also have ambassadors ready to hand those out. Yeah, there's the other one.
I'm supposed to put this on.
Outside this room, so directly outside the doors, they will have tickets for those shows. If you don't have time to go to a planetarium show, please do stop by one of our other activities. Our telescopes are open for looking at, if not looking through. And we have our worldwide telescope and 3D printed telescopes in the elevator lobby. I'll have a map up of those as you leave the room. Please do return your feedback forms with some cookies at the front. Thanks again to Darsh.
Thanks, guys.